Swayam Prabha. Digital India. Educated India.
Good day to all of you. We continue our discussion on disposal of tailings and coal ash in slurry ponds. So today we will be focusing on the planning and design of slurry ponds. That means how do we decide the layout, how do we decide the drainage and the decanting arrangements, how do we decide the stability of the side slopes, what heights we can reach. So these are some of the factors that we will cover. So mostly we will cover the geotechnical aspects of the design, and we will also touch briefly on the other aspects. So I am going to use the word slurry ponds. Mostly what is presented here relates to ash, coal ash disposal, but it is equally applicable to mine tailings disposal. And when we are discussing slurry ponds, we are basically looking at lean concentration slurry disposal. That's what is prevalent in most of the ponds today in India. So slurry ponds can have two types of retaining structures: water retention type dams or incrementally raised embankments. We will discuss both of these and compare these. When you incrementally raise the embankments, they can be by the upstream method, downstream method, or the central line method. We will look at the layout of these ponds, the water balance, the most important thing, how much water is there in a ash pond or a tailings pond, because the higher the water, the higher the phreatic line, and that does affect the stability of the embankments. We will look at how we handle stability. We will also look at how sedimentation occurs and how we decide the size of a pond. And finally, how do we take out the water from which all the solids have settled down. Briefly, we will look at dry mounds as well, some design aspects and some ash placement aspects, and their relative advantages and disadvantages of slurry ponds and mounds. So just to quickly recap, slurry ponds are surface impoundments formed by construction of embankments and related structures all around the area in which the tailings or ash has to be disposed. And we looked at the fact that embankments can be water retention type dams and raised embankments. So there's a tendency to think that slurry is not water, and therefore the design will be different. But because it is lean slurry, predominantly 10 times water in comparison to the solids. So it's like designing a lake. You may operate the ash pond such that water is less and the water is more, but the critical event occurs when water is more. So if you just recall our standard water retention type dams, or what we call earth and rock fill dams, there's a core in the middle and there's a shell and there's riprap and there's a filter and there's a drain. So in a slurry pond, the ponded water level will typically be higher than the deposited material. So such a dam is what one could think that one can adopt. These, if you have to construct a water retention type dam, you have to construct it to the full height prior to the start of discharge. That means you have to make your complete investment in the full height of the dam. So if you want your slurry deposited material to be 20 meters thick, and you want to give a extra freeboard of 1.5 meters. So if you want to have a 21.5 meter high area in which you will be storing your ash or mine tailings, then you have to build this whole dam in one go. And as I said, this is the typical internal zoning which we adopt. In contrast, as I said, it's most of the time one does not want to make those kind of investments in one go, so we used staged embankments or incrementally raised embankments. So they differ from the conventional water retention time dams in that the construction of the embankment is done in stages. You start with a starter dike or a starter embankment, which you construct with locally available material, the local soil. So you usually use the natural soil. And basically the idea is that you should be able to collect 2-3 years of ash or tailings in the impoundment. After that you raise the embankment. And because you are collecting this ash, or because you are collecting the tailings behind the starter dike, that is the most abundant material which is available to you. So economics demands that now stop getting more material from outside. The starter dike is of the natural soil, but the other raisings that you do maximize the use of the material which is available to you in the pond, which is soil-like, and then design it so that you don't have to get more natural soils from outside. So subsequent stages of the embankment are scheduled to keep pace with the rising elevation. We are getting more and more tailings or ash every day, and these stages may be constructed using soil or ash or tailings, but predominantly we want to maximize the use of this. Of course, if the tailings are rendered as hazardous, then you can't use them in the making of the embankment. But as long as they are non-hazardous, you can use them. And I already talked about that we have 3 methods. And the 3 methods look like this. This is your starter dike, which will typically be made of the natural soil. And then you will start depositing your material. And once the material rises towards the top, you will put the second dike. This will be made primarily of this material. And like that, when this is filled up, then you will make this embankment using this material and then do the slurry deposition. So every 3 years or so, maybe more, sometimes 4 years, you will raise your height. And as you can see, this is progressively moving upwards and inwards, and each embankment is resting on the loose deposit which has been hydraulically deposited. You can compact this, but can you compact this? That's the question. So if I was to say, all right, this is my starter dike, and I have filled up my material up to this level. I want to make my next dike. Let me say I'm making it here. Now, can I compact this? This is, let us say, starter dike was 4 to 5 meters high. I am placing this on because later on, as you fill up, the slurry level will rise. So you're on saturated, loose, hydraulically deposited material in the upstream. So the question is, can you compact this? How do you densify? You can densify this as you put the embankment layers. You can use rollers, and you can do optimum moisture content, gamma D max. So that this material will be dense and strong. The challenge is here. And as I go higher and higher, you can see the challenge. When I'm going to put this, then I have to compact this. And as I go higher and higher, I'm going backwards into the upstream into the pond, and I'm sitting on thicker and thicker deposit. So now if I am making my second stage, how do I compact the soil beneath it? To what depth can a heavy roller compact soil beneath the surface? Take the heaviest roller and the maximum compaction energy that you can give with it. How thick a deposit do you think it can compact? Anybody would like to address that issue? Let me say I have a 20-ton roller. I'm going to increase the compaction energy by giving 20 passes. How deep down do you think it will compact? Any idea? So rollers do not compact to great depths. Please be clear about it. You know, your pressure bulb, or no matter what the weight, if the width of the footing is B, then the significant increase in pressure is up to 1.5 to 2B. We all know that. Now when you have a roller, the area of contact is very small. When you have a roller, in a perfect rigid subsurface and a circular roller, you will have a line contact. But here the roller does go into the loose soil a little bit, so you will have a limited width contact. So no roller is going to compact for you more than 50 centimeters, or say if you are giving vibrations and if it is sand, maybe 80 centimeters. So you cannot compact using rollers anything which is 3 or 4 or 5 meters thick. Then you have to go for in situ densification as per all the other techniques which you may have done underground improvement, like all those vibroflotation, dynamic compaction. They are very expensive techniques, so they are rarely adopted. So in upstream method, the staged embankments or the incrementally raised embankments are resting on soft soil, loose soil, which is hydraulically deposited. To get rid of this problem, the other method is called the downstream method of construction. Now the difference in the downstream method of the construction is that you are moving downstream. This is your first dike made of soil. Then the second one is made above it and towards the downstream side. And then like that, third and fourth. The two important things. If your boundary of the ash pond was here and you started your starter dike here, you can't go downwards. That's an error. So when you want to do downstream raising, you please be well inside the outer boundary of the area which you have acquired for the tailings pond or otherwise. So this is one thing you will please see from the last figure. I start here and I go inward, so I have no problems. But here, if I start here and my boundary is here, I can't construct it. The second is, how much material are we using? How much earthwork are we doing? The cost of a dam or an embankment is the volume of earthwork that is done. One is, how far is it coming from? And secondly, how much compaction you have to do, but everything is per cubic meters. So see, if I have 1, 2, 3, 4 stages of raising, this is the amount of earthwork that I have to do. That's the amount of compaction that I have to do. I go back here, and in contrast, I have to do only this much earthwork. This is a much smaller amount of material. So downstream method of construction is more expensive because it requires more earthwork. However, everything is compact. Nothing is resting on the loose tailings or the loose ash. So this is well compacted and it is stronger. The hybrid method is the centerline method, where part of the embankment sits on the loose deposit, and you see, but most of the embankment sits on the densely compacted material. This requires less earthwork than this. And please remember, the vulnerable slope always is the downstream slope. The failure normally occurs with the downstream slope failure. So if you have the downstream slope, that is basically made of compacted material. That's called the centerline method of construction. It's intermediate in cost and advantages between downstream and upstream methods. Just a quick recap. If I wanted to make the conventional dam in one go, and I said, no, I will do it staged. Professor Datta said, I don't want to make the full investment in one go. Conventional staging is like this. This is stage 1, then stage 2, then stage 3, and then stage 4. So the maximum earthwork would anyways be in the first stage. That would still require a large investment, and a very large surface area would remain exposed. So we do not do staging like this. We do staging either like this, upstream or downstream or centerline. And there are two diagrams here. What is the difference? Here it shows that the upstream, the toe of each stage is at the end of the crest. This is normally not adopted. With each stage, you move backwards. That means you give a little berm here. This becomes like an inspection road for the raisings. And you can have a track or a motorable small berm on which you can go and inspect the performance of your dikes. So upstream versus downstream method, upstream requires low quantity of material, I showed you, therefore it is of low cost, it is simple and it is rapid. It's faster because less quantity of material has to be placed. But you require dry surface for construction, so you cannot construct it when the pond is operational. So you must have two ponds available with you. One pond is operational, the other is drying. When it is dry, you can construct on it. And you do want, if you want your stability of the upstream method, you do want that the coarser fraction of your tailings should be towards the peripheral embankment, so that your raising is on the coarser fraction. Why? Coarser fractions, though loose, are even when they are loose, are stronger because they have larger particle size, and they are free draining, so they don't have pore water pressure build up. So you want coarser fraction to be closer to the peripheral embankments on which the upstream raising has to be done. That means you have to operate your ash pond well. We'll address this issue towards the end. All these loose hydraulically deposited tailings or ash are prone to instability under earthquake due to possibility of liquefaction. So the grain size distribution of the material lies in the range of liquefiable materials, unless of course the coarser fraction is there, which some lateral sorting does take place, but we cannot always assure you that lateral sorting would have taken place in the pond. So there is an issue about liquefaction on the upstream. So if you are in a highly seismic prone area, watch out for this problem. The downstream method of construction requires larger quantity of material, therefore it has higher cost, it is slower construction in the sense it takes longer. One thing which has been missed here is it can be done while the pond is still operational, because you are constructing basically on the downstream side, which is available to you. So construction can be done when the pond is operational. It's stable against earthquakes. Nothing is resting on loose deposit. It has better internal drainage. We'll see this at a later stage. However, space must be available on the downstream side of the starter dike. If you don't have the space, you can't expand on the downstream side. It requires less liner area. We will address this later, but new guidelines of the Ministry of Environment and Forests and new standards emerging globally are requiring liners to be placed at the bottom of slurry ponds. So you will find that the liner area is lower because you start the starter dike on the inside, and the liner has to be in a upstream method. The starter dike is at the outside, so the liner area is larger. In most of our ponds, we are using the upstream method of construction, but then failures are also reported from time to time, and that makes it critical. That makes the design critical. What does a slurry pond look like in plan? It can be a ring impoundment or a side hill impoundment or a cross valley impoundment, much like when we talked about landfills. Depending on whether you are on flat ground or low-lying area, or you are on a hill slope, or you are on a cross valley arrangement. And the impoundment can be segmented, and of course segmented impoundments require greater embankment fill. So basically, if you are on flat ground, you will put an embankment all around, and as you will, if you are to increase this by the upstream method, then the embankments will progressively move inwards in plan. If you are at the side of a hill, your impoundment will look like this. That means here the embankment height will be a maximum. If you have a valley type of arrangement, then you will have a cross valley impoundment like a dam, just like you create a reservoir and you have only one side on which there is an embankment. There are hills and raised ground all around it. Typically, we work with segmented ponds, because if we are going to use upstream method of construction, you should be able to close one and move on to the other. Here we are showing 4 segments, but normally it's a 2-segment pond. That is what we do in India. That means slurry is deposited either in one or in the other. And the factors which are of importance as far as the siting and the layout are concerned, the tailings are coming from a processing area, or the ash is coming from a thermal power station. So how far are you from the thermal power station, or how far are you from your processing plant? And what is your elevation? That means how much do you have to pump up the slurry or pump down the slurry? What is the topography, as I just talked about it? What is the hydrology and catchment area? How much water is going to come into the pond from outside areas? We'll look at that briefly. What is the geotechnical and geological features? What is the soil available? Where is the bedrock? Where is the groundwater table? What are the kind of foundation issues are we going to have? And of course, we are going to look at groundwater quality and seepage and contamination potential. These are the factors which influence the impoundment siting. But typically the issue is, where do you get enough land? Where do you get enough land? So if you look at the water balance in a pond, the inflows consist of, and this is important, it's not a closed container system, it's an open system. So the inflows consist of slurry water, which is coming in from the pipeline. More importantly, also the direct precipitation which falls on that entire area. So when it rains, the rainwater is collected. That also adds to the surface water inside the impoundment. And if you are in a low-lying area, or if you are in a side hill impoundment, or if you are in a cross valley impoundment, then all the runoff coming from the sides will also come into the pond. So this is the inflow. The outflow, of course, is the discharge or the decantation. Some of the decantation may also be treated like a recirculation discharge. We may lose some water to evaporation, some will seep into the ground, and some will remain entrapped in the soil voids or in the ash and tailings voids. So those are the outflows. For your water level to be constant, inflow and outflow must be the same. Otherwise, if the inflows are more, the water level will rise. If the inflows are less, the water will fall down. So excess of inflows is sometimes a problem because they cause accumulation of water. This excess inflows is not a problem in ring dikes. Nothing comes into the into your impounded area from outside because there's a dike all around it. Even if there's a little bit of flood water outside, it won't come in. But in your side hill impoundments and cross valley impoundments, there is this huge issue about receiving the surface runoff. And though your embankment costs are low, we have to make diversion channels. So if this is a side hill impoundment, water will tend to come into this. This is already full with slurry water. So this will increase and you'll need a spillway to handle these flows. Alternatively, you have to spend some money and make diversion channels so that any water coming down this hill slope is diverted to the sides and does not enter your ash pond. This is important because if the water level rises, the phreatic line in the embankment rises, and that gives cause for stability issues and problems which come later. So I talked about the phreatic line. All of you are remembering the phreatic line? Yeah. So just quickly to recall, elementary slope stability of earth dams. So dams can be zoned or homogeneous dams. Let us say I have a homogeneous dam. Typically I may have a homogeneous dam which I use for a lake embankment, 5 meters high. That's my lake. So a phreatic line is the top flow line which develops. Let's assume it's sitting on impervious base, and the phreatic line will tend to develop like this. You know all the ways of constructing this. There's a Casa Grande method. You make a flow net. You can calculate the seepage. This is not a good way of designing an embankment because this will remain wet and soft. And eventually, you'll have piping. So you build in some elements that this doesn't happen. And that's your the entire philosophy of design of a homogeneous embankment. So what do you do for the same problem? Anybody? What will you do so that this doesn't happen? Make a toe filter or a rock toe, or there are different things. Somebody might want to do this with adequate. Somebody else may want to put a horizontal drain. And yet somebody else may want to do this. I hope this is visible to you. Okay, he might want to put a chimney. So if I put a rock toe here, so what it does is the phreatic line gets captured something like that. It's very near the surface still, very near. So if you are looking at stability analysis, you still get poor water pressures, but there's nothing soft at the downstream toe. If I bring this a little inwards, then my phreatic line comes and hits it here. Now I'm farther away from the downstream side. And if I build a chimney drain, and let me complete this diagram. Then I am through the chimney drain. So this is what? A blanket drain. And this is a. So in this arrangement, you have a chimney drain, a horizontal blanket, and a rock toe, right? Here you have a horizontal blanket and a rock toe, and all of them have a toe drain at the end. A toe drain is something which is here. A good design says that you catch this water and take it away. So the further you keep the phreatic line from the downstream face, the more stable the dam, the drier the material. And these are the series of options for controlling the phreatic line in a normal embankment. Okay? So this is I would like to complete this discussion. This is for homogeneous dams, but if I have a core, then really nothing comes to the downstream side. Why is a earth come rockfill or a zone dam better? If for the same case I have a zone dam and I have a core here. So how is the phreatic line? Well, this is shell, so coarse grained material, head loss is very limited, and the phreatic line is like this. And there is a filter and a drain here. So what happens? The phreatic line is really far away from the downstream side. So here also you can think of it as this. So an earth come rockfill dam or a zone dam also keeps the phreatic line well away from the downstream side. So the location of the ponded water with respect to the embankment crest is the most important factor influencing the location of the phreatic line. If you are operating the dam well, if you are operating the pond well, you can keep your phreatic line low. However, if it rains, then it will rise. So since it is an open system, it's not that easy to control the phreatic line. If it is a closed system, I could say, all right, I'll close the valve of the inflow pipe and I'll reduce the inflow and the outflow, but I can't do this in this system. So therefore, critical design always is keeping the water level to the highest possible level, and that means a phreatic line will develop. For the low pond condition, the phreatic line may not affect embankment stability, and therefore a pond is normally stable most of the time, but at the high pond condition it has a strong influence. And the other thing is, as the height of the slurry pond increases, the thickness of the deposit increases and the phreatic surface also increases, goes higher and higher, the pressures build up. And lastly, an important aspect is the permeability of the ash deposit within the ash pond also influences the phreatic line, because ash is deposited in layers, so which permeability is higher, horizontal or vertical? If a material is deposited in layers, that means it gets fine, coarse, fine, coarse, fine, coarse. The horizontal permeability is governed by the coarse material, so the horizontal permeability is more than the vertical permeability. That means the water has a tendency to flow laterally rather than to flow downwards in comparison to a homogeneous material. That also has an implication on the phreatic line. So if I look at this, this is my starter dike, this is my first raising, this is my second raising. In the second raising, if I'm operating with a low pond, right, your phreatic line is far away. Let us say 1, 2, 3, 4, 5, 6, after 6 stages, I'm here. I'm still far away, but my pore pressures are now increasing because the water level is becoming higher. However, most of the dams do get operated where the water level reaches half a meter to the crest. When the high pond level occurs, then the phreatic line is formed inside this, and when that happens, it becomes the critical stability issue. So there's two issues here. If the water was high here, it is still a small height dam. But if it is high here, this is a 20-meter high dam with the water very close to the top, and the phreatic line will give you a wet toe. So that can cause issues. So height of the deposit and the ponded water level are the two critical conditions. And many people will say, no, I can operate it with low water. It's not possible. It's an open system. Today it is low. Tomorrow you are sleeping. There's a huge storm at night. There's a huge downpour. You can't say, I will not have water level which will rise. So to take care of this, we put the drains like in a homogeneous embankment, which I just talked to. But do see this, that even if I put the drain in the middle of the upstream side, if my failure surface will tend to go through the loosely deposited material, the critical failure surface will go like this. There will still be pore water pressure. Okay? Whereas in this case, in the downstream side, the failure surface will go like this, and the pore water pressure will not be a much issue. So in the downstream method, you are able to keep the phreatic line well away from the downstream face, whereas in the upstream method, there is always this issue that water is coming out here, water is coming out here, seepage water is coming out here. So a downstream method of construction handles the phreatic line better. Now, we do the stability of these embankments. Why? Because they are reported to fail every now and then. Well designed and well operated ash ponds or tailings ponds, this doesn't happen, but in the others it does. So you remember that for typically design of embankment dams, water retaining type structures, we have three conditions: end of construction, long-term steady state seepage, and rapid drawdown. So which condition is important for staged construction? Which condition is important for staged construction? In staged construction, the rapid drawdown is for the upstream slope, you remember, and the water is supposed to fall from the highest reservoir full level to the depleted reservoir or the minimum reservoir level. So if you have a 25-meter high embankment, it could fall by 20 meters. But in our case, every 3 or 4 meters, the ash is getting deposited or the tailings are getting deposited, so the upstream slope is getting buried. So rapid drawdown can only be for 1 or 2 meters. It's not going to be there for 20, 25 meters. So rapid drawdown is normally not a very critical parameter for staged construction, because the deposited material is burying the upstream slope. Agreed? End of construction is only for the staged embankment. That means staged embankment means each increment of raising 3 meters, 5 meters, 6 meters, the height of the embankment is not very large. But long-term steady state seepage, in steady state seepage, which slope do we analyze, downstream or upstream? Downstream slope. And suppose I have 6 raisings of 4 meters each. How high is my embankment now? 6 raisings of 4 meters each. 24 or 28 depending on the starter die. Now I have a downstream slope which is 28 meters high. It is not being buried by the material, right? So the steady state seepage with reservoir full or the phreatic line very close to the top is the main design critical case. And this may occur once in a year or once in 5 years. You know, it may not occur. If the pond is dry or the pond has got low water level, the embankment may look stable. But when it occurs, then the design should be able to take care that there is no piping, there is no excessive seepage, and there is no failure due to excess pore water pressure. So out of these three, the long-term steady state seepage is the most critical. Others have to be investigated for short heights. Prediction of the phreatic surface location is important. A high phreatic surface reduces stability. Long-term analysis with full impoundment level using effective stress parameters is critical. And as I said, when you will do for the same height of the dam by the 3 methods, your critical failure surface in the upstream method, because this strength is lower than this strength, will be something like this. It will be flatter, but it will be something like this. But for the downstream method of construction, the critical failure surface will be here. This is strong material, well compacted, so issues are not. Similarly, in the centerline method, it will still be here. So in both the centerline method and the downstream method, the issue is about stability of the compacted material. In the upstream method, the issue is about the stability of the hydraulically deposited material, and both from slope stability perspective and also looking at the liquefaction potential of this slurry deposited material. So this design would only be good if everything has been investigated properly. So these are typical embankment sections which one adopts. Suppose I have a tailings pond and I have an ash pond. Starter dike will be of local soil. Local soil means homogeneous embankment, a chimney to keep the phreatic line away. This is a good design. Then I will use most of the ash here. When I use most of the ash here, I'll have to make soil cover so that there is no erosion, no dust fly. You know, if you put fly ash in an embankment, when it is dry, it tends to fly away. It will start creating dust. People will say that it is causing a problem. So the tendency is to put a soil cover over the compacted ash. Similarly, in a mined tailings pond, if tailings are available, first stage it may be made of local soil. This is stage 1. In the second stage, the tailings may be used here, and tailings, the fine tailings also tend to fly away, and so you'll put a soil cover. Okay. There will be a chimney drain, there will be a blanket drain, and there will be a rock toe, as here. Chimney drain, blanket drain, rock toe. But remember, the failure surface will pass like this. So it's basically through dry soil. Here, the failure surface will pass like that. So though there's a phreatic line, still there's a pore water pressure beneath the phreatic line on the failure surface. So these slopes will be flatter, these slopes will be steeper. Typically, these will be 3.5 to 4:1, the average downstream slope, whereas this would be 2.5:1. So these are steeper for downstream method of construction. Seismic stability, as I said, there are two issues here. One is the horizontal alpha H component, which you do for like a pseudostatic analysis. So we have to do if you are in an earthquake prone area, you have to do pseudostatic analysis, and you have to get your stability values within above the minimum acceptable factors of safety. That means the factor of safety of your embankment should be above minimum acceptable. And you remember what's the minimum acceptable factor of safety for a static case without earthquakes? 1.5 is the normal acceptable factor of safety. We must have that. And with earthquake, if you are using the pseudostatic method, the factor of safety acceptable is lower. How much? 1.05, 1.1. So both these conditions should be met. But the third condition, so the pseudostatic method is fine, but the third thing that you have to analyze is the liquefaction analysis. You can use the seed and Idris approach of finding whether your tailings will liquefy, and if they will liquefy, to what depth will they liquefy, because your embankment may be stable, but during earthquakes you may have possibility of liquefaction. So this has to be investigated in detail. So you have to do a liquefaction analysis for seismic stability. In all these conditions, phreatic surface will remain the most critical. How high is your highest water level in the pond? How high is your highest phreatic line in the embankment? That will govern your stability. The other aspect is about sedimentation in slurry ponds. Now, sedimentation in slurry ponds is a hydraulic aspect. We are really not bothered about it. The only thing which I want to bring to your notice is that when a particle enters the pond, and this is an idealized tank which I am calling a pond of depth D, length L, and width W. Then as this particle moves forward with the forward velocity, it moves downward with a downward velocity due to its weight. And you remember Stokes' law, you remember hydrometer analysis, so we can find out that what is the terminal velocity of that particle. And what we want is that by the time the slurry has moved from this end to that end, this particle should have fallen down to the depth d so that it does not come out with the overflowing water. So it's a relatively simple computation about the kind of areas that you need. We are not going to go into detail about this, but one of the equations which govern is the velocity of the particle in the downward direction is the inflow divided by the area. From the Stokes' law, you know the terminal velocity. You can find out, if you know your Q coming in, you can find out your area as Q by Vp. So the finest particle will have the lowest V and it will give you the highest area. So to catch all your fine particles, how much is the area you require, you do it through a sedimentation analysis. And typically, you believe me, when you do these computations, you are requiring areas of the size of 2 kilometers by 2 kilometers or 1.5 kilometers by 1.5 kilometers for adequate retention time. This diagram we have already done earlier. Once we do work out the area, we make 2 ash ponds, one working at one time, the other working at the other time, and we decant the fluid through this. So when we say that I need a travel length of 2 kilometers by 2 kilometers, what I mean is from this point where I am discharging my slurry to this point where I am decanting my slurry, that means from here to here, I must have adequate length of flow that my particle settles down and does not come out. If I have an ash pond which is smaller than what I need, the fines are going to come out. And that's what happens because of restrictions of areas. You don't have much, so the tendency is some of the fine material tends to go away. So we'll stop here at this point, and we have to look at one more aspect, and that is the decantation arrangement. Once the slurry water has come in and the particles have settled, how do you decant the water? And that we'll do in the next class. But if you have any questions, I'll be happy to answer. So we've seen what are the different layouts or plan views of the ponds. We've seen how we raise them incrementally. We have identified the critical issues in the stability analysis. We have recognized the role of phreatic line being very critical to stability, and how the internal drains keep the phreatic line away from the downstream face, and as long as we do a good design, it's fine. But there are many old ponds in which the starter dikes did not have a internal chimney drain, and we have constructed them. They have gone higher and higher, and that sometimes leads to a problem, and how can we remediate that situation, we'll take up in the next class. Any point which bothers you?
Why don't we consider the seepage under the...
So the question being asked is that I have shown you all this, why don't I consider the seepage under? Whether the water is seeping below or not will depend on what the embankment is sitting on. But I'm just going to focus on stability, okay? If this is my critical failure surface or this is my critical failure surface, then factor of safety is resistance over driving, whether it's resisting moment over driving moment or whether resisting force over driving force, resistance over driving, right? And that's along this failure surface. When I compute the driving, what is the main contributor to the driving? The weight and the slope angle. Just make it into a simple infinite slope. If something wants to go down, it's W, and the downward component of W is the driver. The normal component of W, tan phi dash, we are looking at C dash equal to 0 materials. We all recognize that both for tailings and for ash, C dash is 0. So the normal stress tan phi dash is the resisting. The resisting force goes down because of pore water pressure, right? If the pore water pressure is formed, I'm going to do my stability analysis. What is my pore water pressure going to be determined by here? that's the phreatic line, and that's the point on which the stability. So it's about the phreatic line on the top. So seepage from below will change the amount of seepage that is occurring.
Piping on the other side.
Yeah, that's a different issue altogether. That's not a slope stability issue. So the question being asked is, if you are on a pervious foundation, then there will be seepage through the dam, and then there will be seepage beneath the dam. At the moment, I am bothered about the seepage through the dam because I don't want the dikes to fail. Right. If you have seepage below the dam, first question is, does it affect the factor of safety? Unless the seepage below the dam changes the phreatic line, and it is not going to make it rise. Suppose I have gravel at the bottom. Always quickly make this simple. Suppose I have gravel at the bottom, what will happen to the phreatic line? It will drop. So it will only add to your stability of the embankments. When the phreatic line drops, it can drop here. So as far as the slope stability of the embankments is concerned, that's not a concern. The second issue is being talked about is, if water is flowing underneath the embankment and is coming out on the downstream side, it can do piping, right? So how do we handle that? Flow beneath a weir is the ideal case to examine this problem. No water can go through the top of the weir, all water goes from underneath. So how do we tackle flow beneath a weir? How do we prevent the toe of the weir having a problem? If your hydraulic gradient is high and it will cause piping and upward flow will cause a problem, first you have to put an inverted filter at the toe. So that's the answer. An inverted filter at the toe will not allow fines to get washed out. If your exit gradient is large, then you put a vertical cutoff. What should be your exit gradient? 1 by 5. So if you have an issue now there that you find that your exit gradient is coming more than 1 by 5, which is a factor of safety of 5 in it, by the way, then you would like to put a vertical cutoff wall. What will happen when you put the vertical cutoff wall? The length of flow will increase, the exit gradient will go down, and it will go down to below 1 by 5. So flow beneath the dam has to be treated like that. Flow through the dam is the one which affects the stability of the downstream slope. So we have been focusing on stability of the downstream slope primarily because of this reason.
So do these fail completely 3/4 this slide, or it is local?
We will have a look at the question being asked is, what is the type of distress that you see in this slide? Does the downstream slope fall? Does one dike fall? Or do 2-3 dikes fall? We'll have a look at it. We are going to have a lecture on type of failures and remediations. But believe me, once embankment of a ash pond or a tailing pond begins to move, it begins to move in a big way, and the slurry comes out like water. It's not a small failure. It may move down several hundred meters down, and tailings dams have moved 2 kilometers. The slurry has gone out like water. So the whole, there's a breach in the embankment, as you may say. Okay? So we'll stop here, and we'll take up the decant tower and other arrangements in the next class. Have a good day.